So today is our last LabVIEW meeting, and next week is your LabVIEW exam. It's going to be the same format as you did your T-SPICE exam. I'm going to post the exam paper at 5:30 next week, and you will have to create the systems that I will ask you to create in the exam file, and you're going to submit the VI files similar to how you're submitting your homework. And once you're done, then that's about it. There is no class meeting next week. It's just the exam. So today what we are going to cover are the last few topics in LabVIEW. We are going to look at matrices in LabVIEW, arrays in LabVIEW, and we are going to look basically how to create graphs in LabVIEW.
Excuse me, Professor.
Yes.
I sent you an email on Canvas. I'm stuck in traffic right now, so I'm gonna. I'm just letting you know. I'm gonna probably be home sooner, but I'll explain that again.
Yeah, that's fine. I'm recording the session, so that's fine.
Thank you very much.
Yep. Okay, so let me go to LabVIEW and then let's discuss first matrices. So I hope everyone know what matrices is. Is there anyone who doesn't know what are matrices? How do we use matrices? Addition of matrices, multiplication of matrices, subtraction, all those things. You guys are familiar with matrices? I hope so. Okay. All right. So again, since you're familiar with matrices, I'm not going to go into what are matrices. Matrices are simply a way to represent data in rows and columns. You can have a single row matrix, a single column matrix, which generally we called arrays in or vectors in MATLAB, or arrays basically in LabVIEW. Or you can have multi-dimension matrices, two-dimension, when you have both rows and columns with the index of rows and column more than one. You can have three-dimensional matrices, so you have rows and column, and then you have depth as well, stacks of rows and column in depth. We are going to limit our discussion to only two-dimension matrices right now in LabVIEW, and that's what we use mostly in the undergrad, at the undergrad level, two-dimensional matrices. We don't really go to three-dimensional matrices in the undergrad level, at the undergrad level. Perhaps in the electromagnetic fields class, we might discuss three-dimensional matrices, but not in any other of the classes. But we don't have electromagnetic fields class in our program. So matrices and arrays, list, tables, all of these are present in your, let's see, data containers under modern and data container. So you can see real matrix, you can see complex matrix, you can see arrays, you can see cluster, set, map, and so on and so forth. The only thing that we are going to use right now are arrays and matrices. So matrices look like this. By default, it will show you a 3x3 matrix, 3 rows and 3 columns. And you can extend this. You can just go on the side and then stretch it. And you can see as many rows or columns as possible. But again, if you have too many rows and too many columns, then instead of looking at all those rows and columns at the same time, you can just use the indices of rows and columns and jump to the specific row or a specific column. The top index is for rows and the bottom index is for column. And observe that the index starts at 0. So the first row actually is the 0th row. And the first column, the index of first column is the 0th. It's not 0th row, it's still the first row, but the index for that row is 0. And likewise, the index of first column is 0 as well. When we will discuss matrices later on in MATLAB, next software that we are going to discuss after the exam, in MATLAB, index starts at 1. So the first row has an index 1, and the first column, it has the index 1. It does not start with 0. In Python, indexes start at 0. So some programming languages, the index of matrices or arrays, they start at 0. In some programming languages, it starts at 1. In LabVIEW, it starts at 0. So you have a 3x3 matrix. The index of the first row is 0, the index of the second row is 1, and the index of the third row is 2. So if you want to access, for example, this third row and the second column, then the index of that is going to be first the row, which is 2, and then the column, which is 1. So it's going to be 2, 1. So 2 is going to be here, and 1 is going to be here. Now, how do you manipulate matrices? It's very simple to manipulate matrices. If you want to add matrices, subtract matrices, then the two matrices should have the same number of rows and column if you're adding them together or subtracting them together. If you're performing matrix multiplication, then there's a condition for matrix multiplication. Anybody remember that condition for matrix multiplication that you want to share? If you're multiplying two matrices, let's say A cross B, and this is the matrix multiplication, what is the condition for A and B to be multiplied using matrix multiplication? Anybody remember that? Anyone? Nobody remember? I thought you guys said that you are familiar with matrices. Go on. No one? Okay, let me write this down and maybe somebody remember it. Columns and rows. What is the condition on columns and rows of matrix A and matrix B?
I'm just going to take a crack at it. Is it that they have to be diagonal from each other in order to multiply?
No, not diagonal. Columns of the first matrix, that if you're multiplying two matrices, columns of the first matrix must be equal to rows of the next other matrix in order for them to multiply using matrix multiplication. Remember, this is not the normal element-wise multiplication. This is not the first element of the first matrix is multiplied by the first element of the next matrix. No, that's not it. That's called array-wise multiplication. This is the matrix multiplication. So if you're performing matrix multiplication, the columns of the first matrix must be equal to the rows of the second matrix. So for example, if your A matrix is given by 2, 5, 7, 8. So you have two columns. And if your B matrix is given by 1, 6, 7, 8, 9, 2. Then you have two rows. So you have two columns and two rows. And now you can multiply A cross B. And when you multiply A cross B, and this is called matrix multiplication. So you have 2, 5, 7, and 8 multiplied by 1, 6, 7, 8, 9, 2. So the way you do matrix multiplication is you start with the row of first matrix and multiply it by the column of the second matrix, and then you add the corresponding elements. So 2 times 1 plus 5 times 8. So the C matrix, the first element, the first row and first column, 2 times 1, 2, 5 times 8, 40, so 42. And then you do the same with the second column, first row of A, second column of B. So 2 times 6, 12, and 5 times 9, 45. 12 plus 45 is 57. And then you go the first row again and the third column. So 2 times 7, 14, and 5 times 2, 10. 14 plus 10 is 24. And now you go the second row and again multiply each column of B. So 7 times 1 plus 8 times 8. So 8 times 8 is 64. 64 plus 7, 71, right? 64 plus 7, 71. 7 times 6, 42. And 8 times 9, 72. So 42 and 72. 4 and then 4 and 7, 11. So I think 114, right? 72 plus 42. And now again, second row and the third column. 7 times 7, 49, and 8 times 2, 16. So 49 plus 16 is 65. 50 plus 15. So that will be the matrix multiplication, the result of the matrix multiplication between A and B. Again, the condition is that if you're performing matrix multiplication, the rows of the first matrix must be equal to the column of the second matrix. And the resultant matrix will have the same number of rows as the first one and same number of column as the second one. So the resultant matrix, which you see here, has 2 rows, which is the same number of rows as the first one, and 3 columns as the same as the number of columns of the matrix B. So matrix addition and subtraction requires you to have both matrices that you are adding or subtracting to have the same number of elements, and then the corresponding elements are either added together if you're adding them or subtracted from each other if you're subtracting them. But matrix multiplication requires you to have the first matrix to have the same number of elements, to have the same number of columns as the rows of the second matrix, and the resultant matrix is going to have the same number of rows as the first one and same number of columns as the second one. So to give you an example, let's say this is my matrix A, and this is my matrix B. And I want to multiply these two matrices. So let me put a multiplication sign over here. And I want to assign this result to my equals another matrix where I will hold the result. So I'm going to put another matrix and put it here. And this is going to be my matrix C, which is A times B. I think you can see it, so I don't have to increase the font. Okay, so again, as soon as you're going to put the matrices, the 3 blocks are going to appear, A, B, and C. And to multiply A and B, once again, it's important that A and B have the same, the A has the same number of rows, same number of columns as B. So I'm going to go ahead and enter A, which is 2578. So to enter, you just go ahead and put 2, 5, 7, and 8. Now make sure if whichever numbers you're entering, the background is going to get white. And the one that you don't enter, those rows and columns will still be grayed out. That means those are not part of the matrix. So I can just reduce the size to 2 by 2 because that's our size. Now, if your matrix is not that big, I prefer to remove the index display because all the values are already being displayed. I remove the scroll bars, vertical and horizontal. So my matrix is just this. I don't have anything else. And likewise here, my matrix B, I have 1, 6, and 7, and 8, 9, and 2. And once again, I'm going to reduce the size to 2 rows and 3 columns. And I'm going to remove the index display as well as the scroll bars, vertical and horizontal. So it's kind of clean look for this program. And the output I'm expecting to be 2 rows and 3 columns. So I'm going to do that as well. I'm going to go ahead and reduce this to 2 rows and 3 columns. And again, I'm just going to remove something that I don't need. Oh, one thing. When you put the matrix, by default, it is a numeric control matrix because you can see the arrow on the block. It's on the right-hand side. So each matrix, when you put it, is a numeric control matrix. if you want matrix to display numbers, you have to make it as an indicator, like you did for the, for numeric control and numeric indicator boxes. So to convert a matrix into an indicator, you have to right-click on the matrix, and then you have the option of change to indicator. So make sure you change this to indicator in order for this to display your result. And your arrow is going to move on the left side of the box, as you can see. And again, now you can go ahead and it's not showing me. Matrices are a little bit strange because it has an element inside an element. So visible item, now it is showing me index display and vertical scroll bar and horizontal scroll bar. So I go ahead and remove again. Oops. Now it is showing me element only and horizontal scroll bar. Okay. So now I can, I just want to keep only the rows and columns that I need. And that's what I have right now. Now to multiply two matrices, once again, you must satisfy, first of all, the rule that columns of A must be equal to rows of B. If not, then it's not going to let you multiply them together. It's going to disconnect the wire. To multiply them, there are two ways to multiply them. And the reason we're discussing multiplication because it's used very commonly in engineering, matrix multiplication. Under mathematics, of course, you have the multiplication. You can do that simply. Multiply. And observe when you connect it, the wire is thicker than usual data because you have multiple rows and columns flowing through these wires. So the thickness of the wire represents how much data is flowing through that. And likewise, you connect it to this. Now, again, if your matrices are not comfortable for multiplication, then you're going to have disconnection of wires. And when you run it, then you are going to get your result 42, 57, 24, 71, 114, and 65, the same one that we got. There is also another box that is used for specifically matrix multiplication, and that is, let's see. I'll forget where it is. Let me see. In mathematics and linear algebra and A cross B. So this box A cross B also represent matrix multiplication. So if you want to put this box instead of your matrix, then that will also work. So this is A cross B. And that will give you the same result, of course. Now, why there are two different functions, multiplication and a dedicated multiplication block? The reason we have two different functions is for matrices, they operate the same way exactly. If you have matrix block, both of them are going to operate the same way. They're going to multiply if you have the same number of columns and stuff. By the way, let's see, you have two columns, and let's say you delete. By the way, how do you delete row or matrix or vector or column? If you click on the matrix and if you go to data operations and you have the option of deleting row, inserting row, all those options are here. So if I delete the second row, then it will become, of course, grayed out. That means that row is no longer part of this. And once you do that, of course, it's not valid. So you're not going to get any result. It's not valid because, again, number of columns of A is not equal to the number of rows of B. So nothing is going to show up. So you can always, and if you want to add anything, then of course you can always expand it and then write down and add something. That's not an issue. So this is matrix multiplication. Again, two blocks are used. And the reason there are two blocks, as I was mentioning, for matrices, they're the same. They operate the same way. But when you do arrays, with arrays, you can do array-wise multiplication. Array-wise multiplication is that you are multiplying the corresponding elements of two arrays which have the same dimension. So if A and B both are 2 rows and 2 columns, and they are arrays instead of matrices, then you can perform the array multiplication. That is, the first row, first column of array A is multiplied by the first row, first column of array B. The first row and the second column of array A is multiplied by the first row and second column of column B. So you can multiply the corresponding values at the corresponding indices. That you cannot do with matrix multiplication. So if you use the multiplication block with arrays, it is going to perform array-wise multiplication. That is, it's going to multiply corresponding elements. But if you want to use arrays as matrices and perform matrix multiplication, and for that, of course, array A must have the same number of columns as the number of rows in array B. But if you want to use arrays as matrices and you want to perform matrix multiplication, then this block can be used with arrays. And that's why there are two different blocks. Multiplication block can be used simply element-wise multiplication with arrays, and this block can be used for matrix multiplication with arrays. Yes, Samir. Samir, go ahead. Samir, your hand was raised. You were going to ask something? Oh,
I was muted, sorry.
Yeah.
It's not really relevant to what you're saying now, but it was more related to the homework. I have a question about the integrated circuits. I just picked the most similar looking one. I'm familiar with the not and OR gates, but like some of the one that was the and or, I guess, whatever it was, with like the like the D with the line at the end, but it had like a little drawing on the inside. But that was the only option. So under Boolean, if you go to Boolean to the top, so where you're at comparison right now, you go to Boolean, they're going to be there. So like in the diagram in the homework for the last problem, where you have 3 Boolean switches to figure out like what you're going to get on and off. So I know like some of them, like for example, not exclusive OR was one of the options. Like but in the middle, we didn't have that in the picture. Does that matter? So like the little symbol inside of it was not there on the diagram, the little symbol.
Right. I mean, the picture can be a little different as long as you're using the same gate. So this is XNOR gate. Okay. Not exclusive OR is XNOR. As long as you are using XNOR, if I go back to, let me go back to my notes real quick. So here, of course, this is a NAND gate, this is a NOT gate, this is an OR gate, this is an XOR gate. So XOR is 7486 right here. And then this is an XNOR gate right here.
Yeah.
So this is the same as not of exclusive OR, XNOR.
Okay. And then my second question was the only problem I struggled with for the homework was when we had like the LED question, and there was 3 different LED indicators. I couldn't get the first 2 to work, obviously, but then the third one, I had trouble with the logic, trying to wire it. I did the best I could, but will that be on our exam? Should I have to worry about that, like trying to figure that out, or?
So I explained the logic last time and it tells you the logic.
I mean, I used an AND gate like you told us, but I couldn't get it to work for some reason.
Well, A is greater than B and A is greater than C. Both conditions are met, A light is going to be on. Likewise, B is greater than A, B is greater than C. If both conditions are met, B light will be on. And same goes for C, C greater than A and C greater than B. That's the logic. That's the logic of this program.
Yeah, I mean, I understood like the logic behind it, like the mentality behind it. But like I tried doing it like that, like how you were saying to do it like that, and I would wire it. I just couldn't get them to work individually. Like, it would be connected to a different one for some reason. Maybe I wired it incorrectly. But
I
then on the
know.
homework, I just submitted it. However, I tried. I mean,
Yeah, I'll check when I check the homework. Then I give you feedback as what was
I
incorrect.
probably erased it and did a worse job trying to, submit it. But it's okay.
Yeah, well, I'll give you feedback, of course, when I create the homework. Okay, so let's go ahead and delete all this annotation that I have. All right, so let's go and see. So addition of matrices, as I said, is simple. Both matrices should have the same rows and columns. All right, one of the applications of matrix multiplication is evaluation of unknown variables from linear equations. So you have three linear equations in front of you given, and you give me 1 second. And you have to solve for x, y, and z. That is, these three equations represent equation of three lines in a space, and you want to find the point at which these three lines are intersecting in this space. So that's the solution of this equation. In engineering or in math, basically using matrices, you can write these equations down in terms of matrices as it is shown right over here. So if we call this matrix A is the matrix of the coefficients of x, y, and z, 2, 5, 6, 3, 6, 2, and 8, minus 5, and 1. And if we call this matrix X or column vector X, because it's a column vector because it has only one column and three rows. So whenever you have one column or one row, we call that entity as a vector instead of calling it a matrix. But it is a matrix with three rows and one column. Dimension of this matrix is 3 rows and 1 column. And then you have on the right side constant vector on the right side, which is what we call C or K, whatever, constant vector. Now, why we can write these equations in terms of matrices like this? Because number of columns of A are 3, and number of rows of matrix X are also 3. So you can multiply them together. 2x plus 5y plus 6z, which is the first equation, equals to 2. 3x plus 6y plus 2z equals 1, and 8x minus 5y plus 1z equals 4. So these equations can be written in matrices form as it is shown here. And this is important because when you're taking circuits class or any other classes and you're solving linear equations, then you can use programming languages, MATLAB or C++ or Python, or even LabVIEW, to quickly solve linear equations, because you have currents, you have voltages, and you're solving for those current and voltages from 3 equations, 4 equations, 2 equations, whatever. So you can solve those equations using matrix inversion method. So this is called matrix inversion method. There are other methods to solve linear equations. Anybody remember other methods to solve linear equations? Any other method that you remember from your earlier classes to solve linear equation? It is discussed, of course, in I don't know which math class, but some math class it is discussed. But anyone wanna elaborate on any other method that you remember to solve linear equations?
Elimination method.
Elimination method, very good. Elimination method or substitution method, I think it's the same method. Basically, you write down x in terms of y and z from the first equation, which will be 2 minus 5y minus 6z over 2. And then you plug this in the second equation for x. So you will have the second equation in terms of y and z. And then from the second equation, you write down in terms of y, and that will be a function of z only. and then plug in both x, y, and z, x, y in the third equation. And then you will have only z written in the third equation. And you calculate the value of z from the third equation. Then you take that value, calculate y from the second equation, the equation that you wrote, and then you calculate both z and y value and calculate x from this equation. So that's the elimination or substitution method. That's pretty much the first method that we discuss in any math class to solve linear equation. It's a longer method, especially if you have more equations. And then there is an other method that anybody remember that we also discuss in, I believe, in MATLAB, we're going to discuss that method. But if anybody remember another method that you might have discussed in circuits class or any other class. Another method that, again, you might have discussed it is called Cramer's rule. Anybody remember? Does this ring a bell, Cramer's rule? Anyone remember it or no?
Heard of it, but I don't remember how to use it.
But you used it sometime, right? Okay. So Cramer's rule is faster than the substitution method. And Cramer's rule, basically, when you are finding the value of, let's say, x, you create determinant of the coefficient matrix in the denominator. So 2, 3, 8, 5, 6, -5, 6, 2, and 1. That goes in the denominator. And in the numerator, you replace the column for the variable that you're solving for by the right-hand side column and create another determinant or create another matrix 2, 1, 4, 5, 6, -5, and 6, 2, 1. And then you take the determinant of the numerator divided by determinant of the denominator. Now, do you guys remember how to take determinant, by the way? Matrix is determinant of a matrix, 2 by 2 or 3 by 3. Just don't remember? Anytime you're learning matrices, like I think what was it, like algebra or some, I don't know which class do you learn matrices. But
Do you multiply in an angle?
No, that's not angle. When you're doing the determinant, for example, determinant of the top, you do 2, and then you cancel out this column and this row, and whatever is left, you take the determinant of that. 6 - 5, 2, 1. And then you put a negative sign, and then take the next value, which is 5, and again cross out its column and its row, and whatever is left, you take the determinant of that. So that's going to be 1, 4, 2, 1. And then you alternate the sign. So you take plus now, and the third value, 6, and then again cross out the column of 6 and row of 6, and whatever is left, you take the determinant of that, which will be 1, 6, 4, -5. So when you have a 2 by 2 determinant, then 2 by 2 determinant is very easy. You cross multiply. If this is A, this is B, this is C, this is D, then you do A times D minus C times B times C. That's the 2 by 2 determinant result. So you cross multiply and then subtract, and then add everything, and that will be your result of X. And likewise, you can do Y. Denominator stays the same. Numerator, since you're solving for Y, the coefficient of Y column is replaced by 2, 1, 4. And you do the same thing. And likewise, when you're solving for Z, again, denominator remains the same, and numerator, coefficient of Z are replaced by 2, 1, 4. And you apply the same. So that's called the Cramer's rule. And it is faster than in general substitution method. It is not that difficult, especially if you're solving 3 equations. If you go 4, becomes a little bit complicated because 4x4 determinant takes longer to solve. But if you're using, of course, a computer, then that's not an issue. Then you can solve it easily. Now, the fastest method that you can use is what we are discussing right now. So the fastest method is matrix inversion method, in which all the variables can be solved in a single attempt instead of going through each one of them one by one. And again, the method, as you can see, the method is what? You first represent it in the matrix form. And then to solve for x, you keep x on the left-hand side and you take matrix A on the right-hand side and perform the operation, what we call inversion of matrix. This is the matrix inversion. So you're performing A inverse. And you're performing matrix multiplication with the constant vector C. So inverse of A multiplied by C, and that multiplication is matrix multiplication. And this is going to give you the value of X, Y, and Z. So this is the exercise actually that you are going to work for one of the submissions for next week. So how you're doing this exercise? Again, you are going to put, like we put 3 matrices. You are going to put 3 matrices. You're going to basically replicate what you see over here. Right here, you're going to replicate this. So you have this matrix, which will be your indicator matrix because it will have your results. You're going to have matrix A, which is this matrix. And you're going to have your matrix C, which is, of course, this matrix. So first, you're going to take the inverse of matrix A, and then you're going to multiply it with matrix C, like we did the multiplication, because matrix A and matrix C, or inverse of matrix A and matrix C. Matrix A has 3 columns, and matrix C has 3 rows. So they are comfortable for multiplication. And once you multiply them together, inverse of matrix A times C, then you're going to get X, Y, and Z as the output of the matrix X. So that's one of the exercises that you're doing now. Where is the inverse block? Inverse block, again, it's in the linear algebra. Let me go and show you. Inverse block is mathematics and linear algebra. And then you have somewhere dot cross B knocker. Determinant is here, by the way, that we were discussing. And then matrix power. Okay, so, oh, by the way, there's also a solve linear equation block that you can solve actually linear equations. Where's the inverse matrix? It should be here somewhere. If not, then it must be in some other. Why inverse matrix is not here? Let me go and find it. Inverse matrix right here. Okay. So inverse matrix block right over here. I don't know which library is this, but I just searched it. Mathematics linear. It is in linear algebra. I don't know. Anyways. So inverse matrix is right here. So you take the input A, passes through this matrix, this inverse function, and it will convert. And it will do the inversion of matrix A. Now, inversion process, again, it's not a simple inversion process like you are inverting every element of A. It's not that process, but matrix inversion is a different process. If you don't know that, you may study it in the math class at the calculus 2 class, basically engineering and technology calculus 2. When you take that class. Or I don't know if you studied in engineering technology calculus 1. I don't know in which class they discuss matrices and determinants and all those. But in one of the classes, they do discuss it. But if you have taken other like math classes, then you may have discussed the inverse matrix method. I don't know. But here you're just using this block to perform the inversion of matrix. And once you do that, you're going to get the A inverse. You multiply it by the column vector on the right side, and the result is going to be assigned to X, Y, and Z. One thing is important when you're using matrices or using arrays or anything. And that important thing is that if you close this program and reopen it, you will see nothing is going to be there in the matrices. Your data is going to be erased. If you want to hold on to your data, which I want you to, so that when I open your program, I will see that you have all the numbers written, so I don't have to enter the number again. If you hold on to that data, then you have to do one thing. You have to go and do right click and go to data operation and do make current values default. Do the same thing with this, data operations, and make current values default. And now when you save it, it is going to save with the values that are in those matrices that you have put. And when you reopen it, those values are going to be intact. But if you don't do the make current values default, it's going to erase values. So when you are doing anything with the matrices or arrays, make sure that if you're entering some data, then make sure you do make current values default. It is given right here as well, make current values default. Because I don't have time to sit down and then enter all the values. Make sure once you enter the values, you get your result, do make current values default, and then save the program. So that when I open it, all these values are there in your program. I hit the run button and it's going to show me the output. So make sure you do that. Do not forget about it. It's given here as well to tell you that this is what you have to do. Now, as I said, this program you can use in circuit analysis. You can use it anywhere you're solving matrices, and you don't have to spend a lot of time tinkling with your calculators or something. We use MATLAB. If I'm teaching circuits or any other classes, then I use MATLAB. When we use MATLAB starting in 2 weeks, I will keep telling you which programs are important so that you can keep those programs. And if you come to the advanced level classes, and if I'm teaching especially, then I will ask you to use those programs in those classes so that they can help you with the problem solving process. Problem analysis and problem solving, there are two different things. Problem analysis is what you are doing. That's what you are learning. Problem solving is easy. Like you're using this, if you know how to write the equation for currents or voltages, then solution can be done using computers. That's not a big issue. But main thing is analysis. All right, and then as I showed you, there is also a block called solve linear equation that you can use, but you're not using it for this one. You can check your result by using the, as I said, use a block and work on exercise 12 again just to check if your results are correct or not. Okay, you can skip this page. And we are gonna go and discuss now graphs, how you create graphs in LabVIEW. Okay, so if you have to create a graph for an equation, let's say you have, so let's assume generating a graph for f of x equals 2 cosine of 5x sine of 3x. For x equals, let's say 0 to 10, or 0 to 10 is okay, 0 to 10 with an interval of 0.1. So let's say you want to create a plot of this function. Let me increase the size so you can read it. generating a graph for fx is equal to 2 cosine 5x sine 3x for x is equal to 0 to 10 with an interval of 0.1. This is what you're doing here. Now, when you're doing this, one way is, of course, that you manually calculate everything and you enter everything in terms of arrays and then graph between x and y, which is, of course, you don't want to do that. What you want to do is first you have to evaluate this expression for this range, and then you have to use a graph to plot that equation. So that's what I'm going to show you, how to do that. In the tutorial, I'm starting from the very beginning, how to do first the basic step and then move on to do the plotting of graphs. But here I'm going to show you the complete thing. And you will, if you understand this, the basic will be very easy. So I'm also going to capture my values for x and f of x into two arrays. So this is going to be my x value, and this is going to be my f of x value. Right, and these are my array blocks. You can see there is nothing in the array block right now. They are grayed out with nothing in there. So I'm going to keep x values here, all of them from 0 to 10, with an interval of 0.1, and the corresponding fx values are going to be here. And then you can go to graph. Graph is present in the modern library. Graph is present in the express library. You can grab the graph from anywhere. I'm going to start with the xy graph. XY graph in the express library or express XY graph from the modern library. So I'm going to start with this. So this is my graph element. Actually, I'm going to put it on the side. So right here. All right. So in the control in the block diagram, of course, you can see X, you can see Y, and then you can see your plot. These three things. Actually, this is going to go here somewhere because I want to just capture the values. Okay. Now, since you are you want to see the values of x and f of x in the array, what you have to do is to fill this arrays with numeric indicators. So if I go and then grab a numeric indicator, numeric indicator, and pull that and put it here, then this array is going to become a numeric indicator array. And I'm going to extend it for some values. Of course, I cannot. How many values I will have? I will have 101 values. So I cannot see all the values at the same time, but I can jump to any values using the index. And likewise, I'm going to grab a numeric indicator and put it in f of x and stretch it. And as you can see, as soon as you put the indicator, then this becomes indicator blocks. All right. So here I'm going to look at all the values that I'm generating between 0 and 10 with an interval of 0.1. And here, the values that will be calculated according to this equation for the corresponding value of x. Those values will be populated in this array. To do a graphing, of course, you need the graphing block, which you have here. But anytime you're doing a graphing, creating a graph, you need a for loop. Not every time, but if you are calculating values using a range, then you use a for loop. So for loop is under structures, programming structures. And like while loop, it will be a small block and you can stretch it. And it's going to look like this. As you used while loop last week, you have a stop button. There's no stop button in for loop because you don't stop for loop. It is going to run as many times as you want it to run. So that is a predetermined value. You want to run it 100 times, run it 100 times. You want to run it 200 times, run it 200 times. And after it is executed the number of times that you want it to execute, then it's going to stop. As simple as that. So n is the number of times that you want to run this loop. This is the loop count. And I is the iteration count. Every time it's going to run, iteration count is going to increase by 1. It's starting from 0. So the first time it's going to run, the count is going to be 0. And then it's going to start 1, 2, 3, 4, all the way up to n minus 1. So if you want to run it for 100 times, then you're going to connect n to 100. And I value is going to change from 0 to 99. So it's going to run total 100 times from 0 to 99. We want to run it for how many times? So we want to run it for x is equal to 0 to 10 with an interval of 0.1, which makes it 101 points. 0, 0.1, 0.2, so all the way up to 10. That's going to make it 101 points. So this is what I'm going to do. I'm going to put numeric constant